Okay, so let's look at now statistics of VLSI design. So while we're talking about all these mismatches and everything, it is important to now also see what do I mean by statistical modeling and all that. So I'm not taking this course on probability and statistics. I'm just giving you a glimpse of the kind of statistics that we need to be aware of when we design in VLSI. Again, we can talk about this in so much detail in a memory design course, because memories are most strongly impacted by statistical variations. But as we go to finer geometries, more advanced technologies, even flip-flops and even every other circuit, in fact, has an impact or sees an impact. But memories being what they are, they see the failures first. Therefore, we talk about it in the memories course. We don't talk about it as much in analog design course, because there are trimming bits, there are reference currents which you would trim, and you would bias the circuit again to the desired point. In memories, you do not have that kind of flexibility again, and therefore statistics become very relevant. And in reality, the same statistics you can apply to any other circuit also. The only thing is that those circuits are not repeated as often. You don't need to go to Six Sigma extents, as we will just see. Okay. So what we are talking about when we say talking about statistics is that if there is a Gaussian distribution, all of you know what a Gaussian distribution is? What is a Gaussian distribution? So you're searching for the definition of Gaussian distribution. You don't need to do that. What do you understand by Gaussian distribution?
Sir, it's kind of in nature that certain if it's a random variable, then the certain probabilities are more towards one in, like, it's a density more in middle, and it spreads out as we go from the mean. Basically, as you go away from the mean, the probability reduces for the random variable you are referring to. It happens in nature also, so it's kind of modeling natural something like that.
So when we set out to model natural processes, we see that, okay, I want to target that. Let us say you're trying to hit a dart onto the bullseye. I always want to go into the center, but I may go a little on the towards the left or right or top or bottom or something like that. And since my target is always the center, you will notice that most of my darts would actually hit close to the center if I have a good hand and I have good practice. But there will still be some darts which would go towards the periphery. In terms of processes, for example, we would say that, okay, I wanted 20 particles to be embedded, bombarded, and then diffused in my source drain region. But not always 20 will be there. At times 21 will go, at times 22 will go, at times 18 will go. So these are variations that will naturally happen in any manufacturing process. And Gaussian distribution models such variations well. Okay. But Gaussian distribution is not the only distribution that we are worried about in VLSI, but Gaussian distribution is the primary distribution because of which our mismatches are introduced in our circuits, in our devices, in our designs. So, for example, we talked about gate oxide thickness. That, okay, there will be places where there will be 2 atoms, there will be 2.5 atoms, or the orientation is such that the gate oxide thickness would vary from 22 to 28 nanometers. That was the micrograph that we saw in the last class. So in reality, since the target was, say, 25 nanometers, most of the samples will be around 25 nanometers. In fact, if you plot the distribution, the probability distribution of the thickness, you will see that around 25 nanometers, that is the center of this curve, there will be maximum number of samples. So let us say this is 25 angstroms, the gate oxide thickness. And up to 68%, 68.2% of samples would exist between plus minus 1 sigma. Let us say sigma was 1 angstrom, so 26 angstrom and 24 angstrom. So between 24 angstrom and 26 angstrom, you would have 68% of your samples. Between 23 and 27 angstroms, you would have 95% of your samples. Between 22 and 28, the measurements that were shown on that micrograph, you would actually have 99%, 99.7% of your surface area having that kind of a range. But there will still be places. There will still be places which would correspond to this remaining 0.3%, where thickness could be less than 22 or greater than 28. Do you get the sense of it? That as you go beyond the nominal, the mean point, the number of samples you will get there would reduce. Have you noticed this in your experience also? Hello?
So as we are moving away from the mean, the number of samples are reducing.
Yes.
Yeah.
Have you experienced this?
Yes, sir.
So when we say that S&M is Six Sigma qualified, what do we mean?
It means that we are allowing, I'm like 99%. I'm like, it's the best case. I'm like, we have this gap of Six Sigma, which consists to the 99% or 99.7%.
Okay. So actually, the Six Sigma, like some of you might have heard, those of you who have worked in the industry for a little while, you might have heard the term Six Sigma approach. Have you heard that?
Yes, sir. Yes, sir.
So this is the Six Sigma that they talk about, plus minus 3 sigma. That is the Six Sigma that management approach talks about. However, when we talk about SRAMs, when we say Six Sigma, we're talking about Six Sigma on this side, one side. And we want to ensure that this nominal minus Six Sigma is also a S&M value which is acceptable to you. Why do we need to go that far?
Increase yield, sir.
Increase
There
yield.
could be many variations. So we need to accept many. There could be many variations. So we need to accept many.
There could be many variations. But
there are
there is
many.
Six Sigma way. Just look at what is the probability of getting something there. 99.7% are within 3 sigma. Why do I need to go to 6 sigma?
So, but there are many cells. I mean, like 1 MB could be meaning 1 billion.
Yeah, 99.7% means in 1,000 cells, how many would not fit?
3.
3, sir.
3.
So in every 1,000 cells, 3 cells would fail. Is it acceptable to you?
The chip would fail. So no.
No. Now, is it acceptable for a management situation? How many projects does a company do, or how many projects does a team, any particular team would do in a year?
20.
10, 20, depending on the size of the projects and the size of the team. Now, 20, what is the probability of failure happening within those 20 if you are qualified Six Sigma of the management approach? If you qualified from this to this, and you have only 20 samples to take, the probability that particular sample will come out of range is much lower, na? Since the number of samples in those management principles or on management practices is lesser, they go to 6 sigma, which means plus minus 3 sigma. Since the number of samples that we have to account for in memories is much, much higher. Suppose I want 99% yield with a 16 megabit capacity. What is the failure? What is the number of failures that are acceptable? So you will see that for a 16 megabit capacity, I need to go to 6 sigma extent to ensure a 99% yield. Because 16 MB means 16 into 10 raised to power 6 into 100. So these many memory cells we are talking about, 100 dies. And of this you say one should fail. So there can be only one failure in these many samples. And that you will see means so many 9s before you get a first 8. And that is why we need to go to plus minus 6 sigma analysis in our designs.
So we are talking of one die out of 100 dies or one cell among all the cells.
You tell me, can this one die or automatically fail? One cell fails in any one die, that die is waste, na? If you want 99% yield, what are you essentially talking about? You are saying that in that 16, not 16 megabit, in that 1600 megabit capacity, which is across 100 dies, one cell fails. Now, in that same die, there could be another cell that is failing. That will not lead to any additional loss of yield. But again, what is the probability that the second failure will also lie on that same die? 1 by 100. Is it not?
Yes, sir.
So, for all practical purposes, you can only accept one failure per 100 dies. So this is the kind of capacity in which I want only one failure.
So So can you give an example? I'm not clearly getting the concept. Like,
okay. So
I understand the 6 sigma part, but why we have moved from 3 sigma to 6 sigma? Is it just because the yield?
So let us say you designed something with plus minus 3 sigma.
Yes, yes, sir.
I have one megabit memory capacity on the chip. One chip.
Okay. Yes,
how many memory cells do I have?
1 into 10 to the power 6 into 100.
On one chip.
Yes, sir.
1 into 10 raised to power 6 is what I have on one chip, na?
Yes, sir. Yes, sir.
So, other 99.73% is the pass rate. How many cells on that one chip will fail?
99.73
is the pass rate for that design. How many cells in that particular chip will fail? One chip only, abhi.
How many cells? So
if this is the pass rate, what is the failure rate? What is the probability of failure? If the pass rate is 0.9973, what is the probability of failure? 0.0027?
Yes, sir. Yes, sir.
So if every cell can fail with the probability of 0.0027,
Okay.
a collection of 1 million cells would fail. How many of them would fail in this setting?
1 million and 2.00027.
0.0027. So that would be equal to 2700 cells.
Yes, sir.
Every die will have 2700 failures. What yield are we talking about?
Okay.
So is it just about yield, or is it just about getting something out functional?
Yeah. Yes, sir. Yes, sir. And in 6 sigma, the number of dies the number of cells which are failing are less.
Obviously, anything that something. So if we are qualifying 6 plus minus 6 sigma, we are ensuring that 99.9999998% of cells are taken care of.
Okay. Okay, sir.
Only remaining are outliers. And in that also you will see every 100th die there is something failing.
Okay, sir. Yes, sir.
Sir.
Yes, Vaishnav.
Sir, I understood this 6 sigma thing, but sir, this is okay for the 16 MB example. This is fine, sir. I mean, one is getting failed. So, sir, but we even design the memory in like GBs also, right? So, in that case, I think 6 sigma is also not sufficient. I mean, we are supposed to go to 9 sigma.
No, for there, then we will go to repair mechanisms.
So
We will
okay,
talk about repair. We will talk about repair. Don't worry.
okay, sir.
But yes, when you verify your designs, you have to verify it for Six Sigma, plus minus Six Sigma, not the management wala Six Sigma. Okay.
So, but like you're saying that even in one die, even if one bit cell fails, my whole die will fail. But sir, like I will have kind of I would have modeled or designed something. Na, ki if my bit cell fail, there are some like other bit cells which can take place of it, or we can use it.
So
I mean,
we've not talked about it yet, not Raghav. So for present understanding, a die, even one cell fails, the die is rejected.
okay, okay, sir.
I'm already telling you we will have some repair. We will talk about repair, not today, probably next class. But
Okay.
if there was no repair, then the die has failed.
Yes, sir. Yeah, one cell fails. Yes, yes, sir.
Sir,
Die has to be
so
rejected. Yes, Vaishnav.
sir, knowing this bit scrambling, is that like repair mechanism, sir?
We'll come to it when we talk about bit scrambling, repair mechanism. Is that okay?
Yes, sir.
So what we are saying is that we have to qualify plus minus Six Sigma. Now let us talk about two additional numbers. What is called as process capability is defined by a number called CP and another number called CPK. Okay. Both CP and CPK have different impact or different convey different kind of information about the process. The first, CP, indicates that the statistical control in the process is good. What do we see? What is the upper specification limit minus the lower specification limit upon 6 sigma of the process? We will just look at what this means. Okay. And CPK instead talks about a different parameter. It says how far is my upper specification limit from the mean and how far is the lower specification limit from the mean. And then you look at it in terms of sigma. Now, what does this mean? Now, process capability means that if your CP is less than 1, what happens? What it means is upper spec limit minus lower spec limit is some value, but your 6 sigma is crossing that value. Are you able to see this? If this is equal to less than 1, means that that your design is crossing this upper spec limit and local spec limit. Therefore, it is less than 1. CP equal to 1, exactly equal to 1 means that plus minus 3 sigma of my curve lies within the specification limit. So the failure rate would be 0.3%. See, what did we say? That plus minus 3 sigma ke beyond, there could be 0.3% number of samples. That was what we just saw. Hello?
That was 0.03, I guess. 99.97 था ना वो.
99.97 था. 99.7 था.
Okay. हाँ, okay, yes.
1000 के अंदर 3 failures होने थे.
Yes,
so 0.3% is samples will still come out of it. That is CP equal to 1. What does CP equal to 2 mean? CP equal to 2 would mean that each side I have 6 sigma extent which is taken care of. That is where I said that CP greater than 2 indicates that the process is in good statistical control. You can think of getting good yield on the memory. Are you able to see this?
So CP is equals to 2 will be our 6 sigma limit plus 6 sigma and minus 6 sigma.
Yes.
तो CP is greater than 2 वाला हम उसको good क्यों बोल रहे हैं?
क्यों? आप बताओ.
अच्छा, और ज़्यादा कर रहे हैं. Okay. Yes,
I'm
sir, yes.
qualifying more than what was minimum required
Yes, sir,
for
yes.
the exam, na?
Yes,
It's
sir,
a good
yes.
process.
Okay, sir.
So now that is about process control. Now what
But
does
anything greater than 1 is also good, right?
Yeah, है ना? So now,
why are we going?
Sorry,
So why are we going for CP greater than 2?
we will just see. Just wait 2 minutes. Let's look at the other parameter which defines process capability. Let us say that I actually have this CP equal to 2. So I have this kind of a Gaussian which is plus minus 6 sigma on each side. But in reality, the process may change, may shift a little to the left, a little to the right. The typical process corner is centered right away on the target. But slow and fast process corners are also there. Is it not? So the slow and fast process corners would be here, or could be here, as they have shown. What does this mean? Suppose my slow corner is here. What does this mean?
So that means that in the lower one we are we are going even beyond minus 12 sigma, minus 6 sigma on the lower side, but nothing on the positive side is covered.
Yeah, so what this means is that all these cells which are on this side of the lobe are getting failed, are getting rejected. So for the SS lot, for example, my yield is 0%, 50% only. Is that acceptable?
No, sir.
No. So the other parameter talks about process capability in terms of how the centering is, how good the centering is. It capable of producing repeatable products. How well can I center it? That is what CPK talks about. Now let us say you kept the CP equal to 1, or you kept CP exactly equal to 2. What happens? As soon as CPK degrades, what happens? As soon as CPK degrades, you notice that your memory yield goes for a toss. Because for memory to function well, you wanted plus minus 6 sigma. Therefore, you would ideally want CP to be greater than 2 and CPK to be less than 1.33. It only leaves more margin for you and allows you better yield. Is that okay? Hello?
Yes, sir. Yes.
So the values of CPK, sir, the 1 greater than 1, can you elaborate on that, sir? And then if
So what is the definition of CPK? Let us look at it. How far is my upper spec limit from mean, or how far is my lower spec limit from mean? So what is happening here? What is my suppose this is my mean, just before mean, before the lower spec limit. It is not even 1 sigma away. What is the value of CPK? Less than 0.33, na?
sir, I mean the upper spec limit would be the value corresponding to minus 6 sigma or the plus 6 sigma.
If it was centered in there, na? Spec limit का मतलब क्या है? चलो, tell me this. What do you understand by spec limit? अगर वो ही नहीं समझ में आएगा तो how will you understand what I'm talking about? What is spec limit?
Upper and the lower bounds for my design for any parameter.
Upper and lower bound. If you violate these bounds, then I would reject the die. है ना? So when I had my process centered here, in between, right in between upper and lower spec limit, I said that my CP is equal to 2, let us say. So plus minus 6 sigma touch the limit. How many failures are we talking about? Very few. 99.9999998% is passing. So very few failures. But now, due to process variations, systematic variations, the length is made a little longer. So my devices are a little slower. My devices are a little slower. Let us say this curve shifts a little to the left. Now what happens? My mean is now closer to the lower spec limit. Are you able to see this? So my CPK, which was 2 initially because mean was 6 sigma away, 6 sigma by 3 sigma is 2. So it was 2 initially. If it is now just 3 sigma away, it has now degraded to
1 sigma. 1. Yes, sir.
Huh?
Hmm.
And at that, you realize that there will be yield loss.
Yes, sir.
है ना?
22%, 23%.
Some yield loss will start to happen.
Mm.
That is why you want CPK to be less than 1.33. Greater than 1.33. Okay? So this is what it is. This is what it means. CPK equal to 2 and CP equal to 2. Very well centered process. In the center of it, good yields. CP equal to 2, so the process control is very good. Random variations are few, but systematic variations are higher. CPK equal to 0 means you've gone for a toss. Even though your process control is very good, random variations are very well controlled, but your yield will only be 50%. Because 50% of the dies are beyond this upper limit. Are you able to see this?
Sir, confused regarding which one refers to random and which one you're referring to static.
So CP refers to random. That says what is the extent of these local variations there. CPK refers to where is my lot position. So this could be the lot positioning part.
Yes, sir. But I got confused because you mentioned the example of length, which we use actually to control random.
Oh, but all devices have like get edged in terms of poly etching happens simultaneously, is it not?
Yeah.
So if poly etching is done simultaneously, then if, for example, you etch the particular die for 1 millisecond more, what happens?
Length reduces.
All the devices will now be towards fast.
Yes.
So length variations, these systematic length variations would lead to systematic shifts.
Got it.
Now, there is also line edge roughness.
Mhm.
That will be minimized if you use large length devices.
Sure. Got it. So
Okay.
basically, CPK is, we can imagine them as FF or the global variations, and they are
How far away from FF lot or something is your upper spec limit or lower spec limit?
like the small circles we imagined in the rhombus last semester.
Yeah.
They are the CP and then CPK are those.
Yes.
Okay, got it.
Okay. So now till now we're talking only about Gaussian distribution, and that is actually the